Hello, welcome back. In this segment, I wanted to solve this problem. We are given an RSA function, encryption function RSA of m, means m power e mod n. E and n are public values of the recipient of the message. The sender will take the m that he wants to send, use the public key e and n to encrypt and send it to the recipient. Okay, the recipient will decrypt it using the decryption function. So I'm going to assume you know about the RSA encryption and decryption function. If not, please watch the other videos or read about RSA basics. The question here is that what is the value of RSA of n minus 1? How do we approach this problem? Well, we can just start writing what are the things that we know. We know this definition. They're asking RSA of n minus 1. So that means RSA of n minus 1 can be written as n minus 1 power e, right, in mod n. Okay, that's basically what they're asking. Okay, mod n. What can we say about n minus 1 power e mod n? We do know from binomial expansion that if we write n minus 1 power e as a polynomial, all the terms of the polynomial will have n except one term. Okay, only one term will not have n. So when we apply mod n, all the n terms will cancel out. So what we are left with is nothing but minus 1 power e mod n. Okay, so what is the next thing we can do? Even if you don't know binomial theorem, you can see that n with mod n will cancel out. This becomes 0. So this is nothing but minus 1 power e mod n. What is e? In RSA, the standard RSA, e is an odd number. Okay, therefore minus 1 power e is nothing but minus 1. Okay, in mod n. Okay, so what is minus 1 in modular arithmetic? So remember, we are working with the modular clock, right? This is the modular clock. We start from 0, 1, 2, all the way until n minus 1. This is n minus 1, right? This is the modular clock. So we could very well rewrite 0 by n, basically. 0 and n are equivalent in mod n. Okay. So when we say minus 1, we have to go backwards from n, which means at n minus 1. Okay. So minus 1 is same as n minus 1 in modular arithmetic world. Okay. So what is interesting now is that RSA of n minus 1 is actually not even encrypting our message, right? We want to encrypt n minus 1. That's the reason why we are calling RSA, but it will not encrypt it for us. Okay, it will just send the plain text. You see here, n minus 1 is the input, n minus 1 is the output. Okay, don't worry too much because there are not many input messages which will have this property. I'm going to talk about how many such messages are there in mod n later. But at this point, I just wanted to show to you that there are fixed points like this. So let's take an example. For example, I've written here a simple program, right? The program is basically using p to be 11, q to be 17, and e to be 3. These are just small constants to just get the idea across, right? N is p times q, and then we know the Euler's torsion function pi, p minus 1, q minus 1. We compute the mod inverse of e comma pi to get the d. That's the standard RSA procedure. And here is the main part of this demo. I would like to be able to print all the fixed points. Remember, fixed points are points that are not encrypted. Essentially, you send in m as a message to be encrypted to the encryption function. The ciphertext you get back is also m. That's basically the fixed point. So let's run it and see how many fixed points are there for this tiny input. So our n is 187, right? And we get how many fixed points? 3, 6, 9 fixed points. Not bad. Only a small, tiny fraction of our input messages are not encrypted. Okay, it's very small portion. So we can try with different values. Let's try with p to be 3 and q to be 17. What happens? You can see here now my n is 51, still a very small 3, 6, 8. Okay, so really small fraction of the message space will be in clear, basically not encrypted by RSA. Okay, but I wanted to show to you some more interesting properties. Just because of the way the modular arithmetic works, if you see, for example, 1 is a fixed point, because 1 power something is 1, you will also see 50 is a fixed point. Okay, so n minus m is always a fixed point whenever m is a fixed point. Okay, this is an interesting problem. Let's say m is 16. What is n minus m? 51 minus 16 is 35, and 35 is also a fixed point. Okay, 34 is a fixed point. What is 51 minus 34? 17. 17 is also a fixed point. So we can say that whenever m is a fixed point, right? If you apply RSA encryption of a message m, and the ciphertext is m for some reason, okay, you could conclude that whenever you encrypt n minus m, right? N is the modulus. I'm using capital N for some reason on this, so I'll stick to that, is equal to also n minus m. Okay, this is a fixed point property. Okay, in RSA, if E is an RSA encryption function, this is easy to prove. Okay, we can prove it now very quickly. So let me quickly prove this. Okay, we are given an RSA function, and we are given also m as a fixed point. Okay, that means RSA of m, which is defined as m power e mod n, right? Okay, and we said m is a fixed point. What will be the value of m power e mod n? Since it's a fixed point, it should also be m. Okay, and now I'll show you that RSA of n minus m will also be a fixed point. Okay, so what is this? This is nothing but n minus m power e in mod n. Okay, so that means we can cancel out the n. What we are left with is minus m, right? What we are left is minus m power e, which is like this, right? Also in mod n, you can write it here. E is odd number in RSA, therefore the minus we can take it out as minus m power e in, again in mod n. But we learned that m power e mod n is nothing but m. Okay, that means we are left with minus m in mod n. Okay, this is mod n. Okay, but what is minus m in mod n? Remember, I was drawing a clock, and I was telling that if this is 0, this is minus 1. So you go backwards. This minus 1 means n minus 1. Minus 2 means n minus 2. That means minus m means n minus m. Okay, so which means we proved that n minus m is also a fixed point, right? Our input was n minus m, our output is also n minus m. All right, that's all. So RSA does have a few input messages that will not be encrypted. Okay, how many? I will talk about it later. There's a nice mathematical formula that enumerates number of fixed points, okay, in an RSA system. Okay, in practice, you will not directly call m power e mod n. You will first apply padding, and then you will call it, but still you will have the fixed points on the padded message. Okay, and there will be a very, very small fraction if you carefully choose the e. If e is chosen to be so close to the prime numbers, then you may have many fixed points. Okay, I will talk about that later, but at this point, this is good enough. Whenever m is a fixed point, n minus m is also a fixed point. All right, that's all. Thank you very much.